Okay, thank you, Peter. Oh, sorry, I'm just going to minimise it. Yeah, so as Peter said, today I'm going to be presenting a spatial emergent constraint on the sensitivity of soil carbon turnover to global warming, which my co-authors and I had published earlier in this month in Nature Communications. Oh, yeah, okay. Okay, so a little background. The aim of this constraint was to reduce some of the uncertainty associated with the feedback of soil carbon under climate change. Because the uncertainties in projected changes of soil carbon storage are key components of the uncertainty in global carbon budgets, which are required for accurate Paris Agreement targets. And not only is this feedback really uncertain, it also has the potential to be very large, which we can see if we look at this carbon cycle diagram from the IPCC report. The carbon stored in soils is at least 3 times the amount compared to atmospheric concentrations. So if even a small fraction of this carbon was to be released into the atmosphere, that could result in a significant feedback to climate change. So looking very simply at how soil carbon changes under climate change, it will be determined by 2 main components. So we've got the increased carbon input into the soil from vegetation and the increased carbon output from the soil via respiration. And both of these fluxes have high uncertainties associated with them. But in this study, we focus on this output flux. So this is to do with under increased temperatures under global warming. The microbes in the soil can decompose carbon at a greater rate, resulting in more carbon released into the atmosphere via the flux known as heterotropic respiration. So to isolate this response, we can define a soil carbon turnover time, which is the time it takes, the time carbon resides in the soil for. And it's defined as the ratio of soil carbon to the carbon pool to the carbon output, which I just said is that heterotropic respiration flux. And soil carbon turnover time is projected to decrease exponentially under global warming. However, there is a large uncertainty associated with this. And this decrease in soil carbon turnover time, tau S, will have a resultant decrease in the amount of soil carbon, which we can see on this figure on the right here. So on the y-axis, we've got this change in soil carbon due to the change in soil carbon turnover time against global warming, so differing amounts of temperature change for a selection of CMIP5 and CMIP6 models. And you can see for each of the models, there's a decrease in carbon with increasing warming. You can also see that there's a big uncertainty here. So at 2 degrees global warming, there's a range of almost 600 petagrams of carbon. So due to this uncertainty and due to the uncertainty having remained across CMIP generations, we try and reduce this looking at a constraint approach. So as many of you know, emergent constraints have been used to successfully reduce the uncertainty in climate change predictions, mostly based on temporal trends and variations. Whereas in this study, we consider a spatial temperature sensitivity. So this is the idea of using a spatial temperature sensitivity to tell you how sensitive a variable is to temperature, which you can then use to constrain the future response to warming. So we start by investigating the temperature sensitivity of soil carbon turnover time, looking at observations. So we can start with a map of observational soil carbon, which you can see on the slide, and a map of observational heterotropic respiration. And then using our definition of soil carbon turnover time, we can obtain a map of inferred soil carbon turnover time. And then to investigate the spatial temperature sensitivity of this, we simply plot this data against an observational temperature data set, which you can see here on the plot on the right. And each of these faint black marks are each latitude and longitude point. And then simply we plot this quadratic relationship, this thick black line here. We plot between these 2 variables, and we say this black line represents the temperature, the spatial temperature sensitivity of this soil carbon turnover time in observations. And we can actually do the same thing again, but using each of our Earth system models. So we plot, we find these quadratic relationships for the spatial temperature sensitivity of soil carbon turnover. And each models here are plotted using these colourful lines. So you can see that there's quite a lot of variation here between the models themselves and then the models compared with the observations, which you can suspect is part of the reason for this uncertainty in the subsequent change in soil carbon. So the idea of this spatial emergent constraint is whether these spatial temperature sensitivities that we've derived can help you predict the subsequent change in soil carbon under global warming. So what we can do is we want to test this by calculating this change in soil carbon due to the change in soil carbon turnover time. And we'll do this twice, but once using model output data and once using these derived relationships, so these model-specific quadratic relationships. And if we do this, so for each of our models, we can use the models to test the premise. So whether we're basically investigating whether these relationships can predict the change in soil carbon. So here is the result where on the y-axis, you've got the model change in soil carbon due to the change in soil carbon turnover time. And on the x-axis, you've got this change in soil carbon due to the change in soil carbon turnover time. However, using these model specific relationships together with model temperature alone. And as you can see on this plot, actually, all of these points for 3 different future scenarios are actually all very close to the one-to-one line, which tells us that these model-specific quadratic relationships actually do predict the subsequent change in soil carbon, as well as the model projections under climate change. So as the premise of our emergent constraint works for each of our Earth system model, this allows us to obtain an observational constraint on our x-axis. So this plot on the left here is it's the same plot again, very similar. However, this time we considered change to be 2 degrees global mean warming. But again, we've got our model change in soil carbon due to the change in soil carbon turnover on the y-axis, and this change in soil carbon due to the change in soil carbon turnover, however, calculated using these model-specific relationships on the x-axis. However, to obtain this observational constraint, we take that observational quadratic relationship, so the thick black dotted line, that because that's derived from observations, we can take that to represent the real-world spatial temperature sensitivity, where we can calculate then the subsequent change in soil carbon using this sensitivity. So we do this using this relationship and then future model temperature. Though obviously we're considering 2 degrees global warming, so the temperature is the same. However, each of the models have a slightly different spatial warming pattern. So hence you end up with this small uncertainty around our observational constraint. And then using this observational constraint together with the observational uncertainty, together with this emergent relationship that you find across our ensemble of Earth system models, you can then obtain an emergent constraint on the y-axis, which is an emergent constraint on this change in soil carbon due to the change in soil carbon turnover time. And you can see this constraint on this plot on the right here, where this black line shows the distribution of projected change in soil carbon due to change in soil carbon turnover time. And then this blue line shows our emergent constraint of new model predicted range, where you can see there's an obvious reduction in the uncertainty there. So just to summarize, so yeah, we focused our constraint on the feedback from soil carbon under climate change, as this is very uncertain, and it's also very important in calculating accurate carbon budgets for Paris Agreement targets. And yeah, we do a spatial emergent constraint, so we use the real world spatial sensitivity to constrain. We found to find an emergent constraint on this response of soil carbon turnover, where we successfully have half the uncertainty in this response at 2 degrees global warming. Thank you.